Now, Hayworth projections are going to be analogous to Fisher projections, at least they are for me, because what we're trying to do is we're trying to represent cis-trans chemistry around rings. Now, the Fisher projection did this by drawing a line and then doing left-right, and we recognized that we were always kind of coiling back. So that line that was vertical was a line of carbons that kind of bent back into the page. The Hayworth is kind of like the next step. Let's say they bent into a ring and we took the ring and put it on its side. Now, again, this is meant to represent cis-trans notation to make it easier to see what's going to happen. So the big thing here is translating a two-dimensional drawing like I have here on this side of the board into a Hayworth projection. So how do we draw our Hayworth projection? Well, the first thing we're going to do is we're going to pick two carbons that are going to be the in-page carbons. They're going to be connected to the page of our paper when we draw it. Now, for a 5-membered ring, we're only going to work with 5 and 6-membered rings, we're going to pick carbons such that there's one between the two of them and two between the others. So basically we're going to try to put carbons that are kind of like in the center of the molecule, that kind of cut the molecule in half. Now for a 6-membered ring, this is pretty easy. These are going to be the carbons that sit 2 carbons away from each other. Now, to start the Hayworth projection, you're going to need to put dots on your page to represent these 2 carbons. So this is this carbon. Draw these in red. These 2 are these carbons. Now imagine if we took these planes and we tilted them. So instead of this being in the page of the board, we're going to turn it so that it tilts out. Same thing's going to be true here. Well, if we tilt it, we're going to have a dark bar, a little happy smiley face here representing the carbons coming out. Same thing's true down here. And our carbons going back into the board, we're just going to draw with a light line. So this ring here and here represent the carbons within our backbone. And we're going to treat them as if these carbons are all planar. Now yes, you probably remember that cyclohexane is rarely planar if ever. It likes the boat conformation. And same thing's true of cyclopentane. It doesn't like this planar conformation. We're going to keep that in the back of our minds. The point of this is not to know the exact geometry. We know these are tetrahedral carbons and we can definitely sit back and say, oh, it's doing this, it's doing this. The point here is to keep track of the cis and the trans, and this is going to come up a bit later when we start actually talking about specific reactions and how we name the sugars with a plus-minus notation. Now, what we're going to do with each carbon is we're going to put a vertical line. This vertical line represents bonds to whatever is attached to that carbon. Now in this case I have nothing but hydrogens. But let's say I were to put OH, 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 and OH. So I've got these polyols, or basically we're building towards our sugars. Well, anything that has a wedge is going to go above the ring. So since this has a wedge and this corresponds to this carbon, our OH group goes here. This has a wedge, it's up, goes here, OH, into OH. Everything else we're going to fill in with hydrogens. And this is how you generate your Hayworth projection. Now, to go the reverse route, it's actually pretty straightforward. Figure out how many carbons are in your ring, draw your ring. Anything that's above is going to get a wedge, anything that's below is going to get a dash, and this is how you draw a Hayworth projection from a 2D drawing and how you go backwards from a Hayworth projection back to your 2D drawing.